So this week we're going to take a look at section 2.4. We'll split it into 3 parts. It's pretty much all about graphing sine and cosine. We start out looking at just the basic graph, and then each day we're going to focus on a different transformation. So we're going to go really slow, break it down. We're not even going to do multiple transformations like in the same day, just one transformation at a time. So sine and cosine are the 2 graphs that we're going to focus on. But first, I want to show you what they look like, and then I'll put up a graph of tangent or some of the other ones. But these are the 2 that we're going to really look at. All right, let's put it in. All right, so the first thing is when we put in a trig function, we want to set the window. And what zoom do we normally use? Like if we just kind of want to reset the screen, and the standard one, right? We normally go zoom, and we do the standard one, which is 6. Well, when you graph a trig function, a lot of times you're going to use 7. Okay, so zoom 7 is a special window that works for trig functions. All right, so let's do zoom 7. And that's what the graph of sine looks like. So let's say it's like a wave.
And you zoom 6 and go straight.
Yeah, if you do zoom 6, it won't look that good.
Why?
Because it's zooming in on such a small part of it that it looks like it's straight. It's like it's an extremely small part. If you check the window out, those numbers are nowhere near zoom 6. Zoom 6 would be negative 10 to 10. This is negative almost 500 to 500, so it's much bigger. But the y min, that's close to the standard one. But the x min and max are nowhere near zoom 6. Okay, so that's what the graph of cosine looks like. And now let me put sine on at the same time. It's pretty similar. But how would you describe the difference?
It's faster.
What do you mean by faster?
It's like it's a little curve before the other.
Okay, so it does everything the other one does, the red one, but it does it like just before it. So we could say that if you wanted to describe that as a transformation, how could you turn the blue one into the red one? You could do a flip. There's something simpler though than flipping it.
Go back.
Do what with it?
Go back one.
Yeah, if you just took a copy of it and just shifted it left 1, right? Well, 1 tick mark. We don't know actually what a tick mark represents, but if you shifted the blue one 1 tick mark to the left, or you take the red one and shift it 1 to the right, then you get the other graph. Okay, so sine and cosine are pretty similar. Let's take a look at tangent. Now, the graph of tangent, it has a pattern to it, a pattern that keeps repeating, but it doesn't look anything like sine or cosine. Yeah, first of all, it doesn't have a minimum or maximum. Tangent goes up to infinity and it goes down to negative infinity. And the other thing about tangent is it's not continuous. Meaning if you want to draw it, whatever you're using, you'd have to lift it up and then start again each time you draw another section. With sine and cosine, you don't do that. You just put your pencil down, keep it down the whole time, and then draw the whole graph. Okay, so tangent looks very different. And secant, cosecant, and cotangent have more in common with the tangent. You have to pick your pencil up to keep drawing different sections. So sine and cosine are the only 2 that looks like waves. And we'll take a look at a couple different things you can do with the waves. One thing we can talk about is sound and different frequencies. So we'll do a little bit with sound frequencies. Maybe later today, tomorrow, or Wednesday. If we have extra time, I'll show you something you can do with sound frequencies in a So we'll see if we can get to it. So sine and cosine, they're a wave, but there's a special name for that. That's called a periodic function. Nothing else that we've studied in this class has been periodic. Lines? No. Parabolas? Nope. We haven't studied any other kind of function that's periodic. Let me take, and let's just make a copy of that where it just has sine. So there's the graph of sine. And what makes something periodic is if the graph repeats itself. So start here. And I stop right there. If I can copy and paste one section of the graph over and over, and I get the entire picture, then that's called a periodic function. So let me take that, copy, and put it right there. That would be the next, it's not called section, I'm going to tell you what it's called in a minute, but that's like the next section of the graph. And then I could do that again. And I get the next section. So that's what makes something periodic. It's a pattern of the graph that repeats itself over and over. So what's happening in that graph is basically the y values are what are repeated. The x values just keep heading further and further and further and further to the right. But the y values are stuck between 0, 1, 0, -1, and 0. 1, 0, -1, 0. 1, 0, -1, 0. I'm not naming every y value, but those are some of the important ones. So it just keeps repeating in that 1, 0, -1, 0 pattern forever to the right and to the left. So it's periodic because all the y values repeat over a given set of x values. In my case, what's kind of the set? It's from here to there. That's the amount of distance you have to travel before you can copy and paste that entire section over and over. Yeah, it's 4 tick marks, but if we look at, let's go back to the calculator and let's see what does each tick mark really represent. Each tick mark on the x-axis represents how much? So what does it say for the x-axis? Each tick mark is how many units? 495, that's the left edge of the window, and the x max is the right edge. No, that has to do with something when you press trace and start moving your cursor on the screen. So you don't have to worry about that. It's the scale. Yeah, scale, like if you draw something on graph paper and you scale your lines to go by like 2s, that's called scaling. So yeah, the scale is what each tick mark represents. Yep. So this is 0. This is 360 degrees. Once you travel through 360 degrees on this graph, you're going to see the same patterns you just saw repeated again. Or if we did radians, it's 0. What's 360 degrees in radians? Something with pi. 2 pi. So yeah, 2 pi. And that's what we're pretty much working with this week. We are working in radians. I might mention some things in degrees every now and then because those numbers are nicer, but we have to get used to seeing radians. So I told you there was a name for that interval. Like I called it a section. It's not really called a section. The amount of distance you have to travel before that graph is going to repeat, that's called the period of the graph. So the length that you travel before the graph repeats itself is called the period. Now, a couple people already figured it out. My next question was going to be, how far do you have to travel before that graph repeats? It's 360 degrees, or 2 pi radians. So on your screen, if you wanted to set this up so you're only seeing one period of the graph, what I would do is start at 0, and where would I end so I just see one period?
360.
I could end at 360. And if I do that, you'll see exactly, that's called one period, or it's also called a cycle. What if I set it from 0 to 720? How many cycles or how many periods would I see now? Yep, you're going to see 2 cycles. There's 1, there's 2. So you can change your screen so you see however many cycles you want. But the idea is when we're sketching it, you only need to sketch 1 cycle. Because if you can sketch 1, then I know you could repeat it and sketch 2. Just copy and paste it. So the period of sine and cosine is 2 pi. Now, we've done transformation, so we know we can stretch that or we can compress horizontally. Let's say I did something like sine 2x instead of sine x. What did I do to get that red one? Did I compress the blue one, or did I stretch the blue one? I compressed it. In fact, I compressed it by twice as much. So now what's happening is it's oscillating faster. So we can change this period. It does not have to be 2 pi. But what I'm saying is if we don't mess with it, it will be 2 pi on its own. I kind of already said this to you. So if you graph sine or cosine, once you get through 360 degrees, the graph just repeats itself. And that was when I showed you I was copying and pasting. I think I already mentioned that too. So another name for a period of a graph is called 1 cycle. Cycle is used quite a bit as a term in other areas. For example, in electricity, there's something that's measured in cycles per second. And cycles per second measures what we call the frequency. Hertz. Hertz is the frequency of the electricity. Has anybody heard of that before, Hertz? So, for example, when you're talking about alternating current, not the kind of current in your car, the kind of current in your house or like in this room. Regular AC current operates at 60 hertz. That means 60 cycles per second. So when you plug something in the US, whatever you're plugging in, it's designed to run on that frequency of electricity. Other countries don't use 60 cycles per second, they use 50. That can make a difference. Now, if you look at like the charger or something like a Chromebook charger, if you look on there, usually it says something like 50/60 hertz. And what that means is there's electronics built into that it can handle whether you plug it in the US or you plug it in another country. It'll work on both. But some older things may not work on both. And if they don't, you plug it in the wrong type of electricity, well, it's not going to work. All right, so to graph the trig function, it's not quite as simple as drawing a line. Okay, if it were a line, I would say you need 2 points. Draw your line and you're good. If it was a shape like a parabola, so you probably need 3 points. But with a trig function, you need about 5. And I call these like the 5 important points, or the 5 key points when you're making a sketch. The beginning, the end, the middle, the high, and the low. If you graph those 5 points, you'll get a pretty good sketch of your function. So those are, when I talk about the 5 points, that's what I mean. Now, let's think about those points for a little bit. We know that we start at 0. And this is a picture of one cycle. Where does the cycle end? It's the same as asking, what's the length of the period in that picture? Yeah. Okay, so it ends here, and how far away is that point from that point? We mentioned this number in degrees, and we mentioned it in radians. Yeah?
360 degrees.
It's 360 degrees, yep. Which is the same as how many radians? Yep. 2 pi. So if we know this point is 360 degrees away from this one, you should be able to figure out how far apart each one of those points is. So imagine just put some lines on here. You've got 1, 2, 3, 4 sections equally spaced over 360 degrees. So how much is each section worth? We actually already saw this in the calculator. Yeah? 90. Each section is worth 90 degrees. 0, 90, 180, 270, 360. And those 4 values mark the quarter points. 0, first quarter, second quarter, which is half, third quarter, and then the fourth quarter, which is the whole cycle. So if we label these at 0, that's pi over 2. That's the same as 90. What about 180? Does anybody remember what that is in radians? Yeah? Pi, good. The next one is 3 pi over 2. And we end at 2 pi. So 0, pi over 2, pi, 3 pi over 2, 2 pi. We're going to say those numbers a lot this week. And I don't know if I mentioned it a lot on the graph, but did anybody notice what the highest and the lowest that the wave went was? Yeah?
1, -1.
It was 1 and -1. Again, I didn't really point that out. But the highest the wave goes is 1, and the lowest is -1. So what we're going to do is we're going to graph transformations. In order to be able to graph a transformation, first thing you have to know is, where did the graph start? That's a pretty accurate picture for sine. All those points are correct. So what I want to do is write down these 5 points in a table. The 5 points that I have for those green dots. Okay, I'm going to make a table for cosine in a minute as well, but let's start with sine. Dominic, what's the coordinate of that first green dot? 0, 0, 0. Okay, the first green dot goes right through the origin. So that is your first coordinate. 0, 0. Okay. Now let's do the second one. Kiana, what's the coordinate of that second green dot? The y value is 1, but what's the x value? These tick marks don't go by ones. Pi over 2, comma 1. Yep, that's your second point. Pi over 2, comma 1. It's really important we get this table right, because if we get it wrong, then every transformation we do based on this table will also be wrong. Okay, so pi over 2, 1. Right. Let's write down the third one. Austin, what's my third point?
Just pi.
Pi, comma.
Pi, comma 3.
Pi 3 would be like up here. Up 3.
Comma -2. I'm not quite sure.
So we're looking at that dot, right?
Yes.
How far up and down is that dot?
Oh, it's on 0.
It's on 0. Yeah. So what would be the coordinate of that point?
On 0.
That's the second number. What about the first number?
2.
You want to help him out?
3 over to the right. 0.
Well, it is 2 tick marks to the right, but each tick mark is not 1. How much is each tick mark here? Someone remind me.
9
Yep.
degrees.
Each tick mark is worth 90.
So 270.
So this one is 1, 2 over.
So each one's worth 90.
Yeah. But we already have the x's labeled, so you don't have to figure anything out for the x. This point is at pi, which is 180, comma 0. So pi, comma 0, that's your third point on that table. All right, let's try the fourth. Grady, what's my fourth point?
3 pi over 2, comma -1.
Yep, 3 pi over 2, -1. That's the 3/4 mark in my cycle. 3 pi over 2, -1. And what about the last point, Sam?
2 pi, comma 0.
Yeah, 2 pi, you've reached the end of your cycle, and you are at 0. So these are the 5 points that make up one cycle of sine. So if we have to shift anything up and down, left and right, stretch something, these are the points we're going to use to do it. All right, let's look at, I'm not going to do it by hand, but let's look at cosine and see if we can figure out the 5 points for that one. Now, we know the y's are still going to be between -1 and 1. The sine and cosine look pretty similar. but it's not going to start at 0. That will not be the first one. So let's put cosine in there. Get rid of that. Right, and we're looking at more than one cycle. Just focus on that. That's the first cycle. Like that. It's still a wave. It's just cosine starts at a different spot, so it looks more like a curve going down. But it's still a wave. And here would be your 5 points. 1, 2, 3, 4, and 5. Okay. So, Fiorella, what do you think my first point would be?
That's like 0, -1.
So 0, -1 would be down here.
Oh, perfect. 0, 1.
0, 1. Yep. That's your first point. 0, 1. All right. Let's go to the next one. Now, we already know the x values because the spacing on these is exactly the same as the spacing on those. You want a point every quarter of a cycle. So 1, what's the coordinates of that second point? Well, let's start with the x value because we know it's going to be the same spacing for the x's for this one as it was for sine. So what's the x value of that second point? Remember, each tick mark here is not worth 1. Someone remind me again how much each tick mark is worth? 90, or pi over 2. So when we get to the second tick mark, we are at pi over 2. And what's my y value at that point? 0. So that second one is pi over 2, 0. You don't have to do these 5 points, but if you do other ones, it's not going to give you as good of a picture. Okay, we always want to get the maximum points, the minimums, and then wherever it crosses the x-axis. Those are the 5. All right, third point. Jenna, what's the coordinates of that third one?
Pi and -1.
Yeah, pi -1. So there's your third point. Gavin, my fourth point.
Would be 3 pi over 2 and -2.
3 pi over
sorry,
2.
0.
Yeah, 3 pi over 2 -2 would be like down there.
Yeah.
So yeah, 0. So 3 pi over 2, 0. And Ryan, my last point.
2 pi and 1.
2 pi, 1. Yeah. So these are what, whenever we do a problem about cosine, these are the 5 points we're going to use because they mark the 5 important spots for cosine. These 5 points mark the 5 important points for sine. So these two tables are everything we need. Okay. Any questions on those two tables? As I said earlier, we are not looking at tangent, secant, cosecant, or cotangent. We're not graphing those. Okay, so when you're doing a transformation, we have to take those 5 points and figure out what's happening to them. Are they moving up? Are they moving down? They're moving left, right? Like what are we doing to them? So a coordinate has two parts to it. It's got the x value, it's got the y value. For every transformation that we do, we are only changing one of the numbers in the coordinate. For example, we might do something like this. That +1 is going to do something. That's a vertical shift. When you shift vertically, it changes the y value, but nothing would happen to the x. That's how every problem is going to be. One value in the coordinate is going to change. The other value is going to stay the same. The only way both of them could change at the same time is if I did multiple transformations in the same problem, like shift up and left or right. We're not doing multiple transformations in the same problem. Okay, we're going to stick with one per problem. So for every transformation, either the x's stay the same and something happens to the y's, or the y's stay the same and something happens to the x's. Now on a test, I'm not going to tell you which one stays the same and which one changes. You have to be able to look at the problem and say, okay, that's a vertical shift. That's going to change the y's. Okay, so that covers pretty much the background on doing transformations for sine and cosine. From now till Wednesday, okay, when we finish up, we're going to look at doing one transformation at a time. And the first one we're going to start with is going to do something like this. Let's see. Could be adding or subtracting, but it's going to be inside the parentheses. Does anybody remember when we do a transformation of any other function? What does adding and subtracting inside the parentheses do? It moves it left and right. It's the same idea if you did this, or if you did something like a parabola. If you put a plus or minus a number inside the parentheses or inside the root, it does move it left or right. Which way would +3 move? Either one of these. Yep, +3 is going to move it left. And then if I had a minus here, it would move it to the right. Yep. Now you might wonder, why did I put pi here? That's kind of a weird number. Well, when we shift left and right with trig functions, even though you can shift by any number you want, there's three numbers that they usually shift by. 45, 90, and 180. Those are the most common amounts to move it. And when we shift it left and right, when we deal with trig functions, they don't call it shifting left and right. It's the same thing as shifting left and right. They call it a phase shift. So a phase shift is what you call shifting left and right in this section. And that's what a phase shift looks like. So you know something is a phase shift if you're adding or subtracting. and it is inside the parentheses with the x. If you don't put parentheses, then it is not a phase shift. If you did this, that is not a phase shift, that's a vertical shift. Has to have parentheses around x and the number. And whether it's sine or cosine, that doesn't matter. Could be either one. The only thing that sine and cosine affects is the table that you're starting with. So you guys pretty much already know the two rules about when it shifts left and when it shifts right. I just asked you all. And we've talked about them a lot when we've done other kinds of transformations. But I'll put them up here again just in case anyone needs them. All right, so what if in parentheses it says x minus a value? Which way is the graph going to go? Yep, it's going to shift to the right. How much is it going to shift to the right? Well, it depends on what the value is. So it'll shift right by that value. And you can shift right any amount you want. But what did I say the common amounts were to shift by? Yep, 45, 90, and 180, or pi over 4, pi over 2, and pi. All right, what about if it's the opposite? What if it's x plus a value? Which way is that going to go? That's going to move everything left. Again, how much? Well, it depends on what you put there. So this is backwards, right? It's not what you would expect. Usually if you picture a number line, right, negative numbers are over here, positive numbers are over there. So you would think if you put a minus, it would move it towards the minus. No, it doesn't work that way. If you put a minus, it shifts it right. If you put a plus, it shifts it left. Okay, so it's backwards. And it's been like that all year. It's always been that for left and right. All right, so now let's think about that in terms of a coordinate. If you took a coordinate and you moved it left or right, don't move it up and down. Just move it to the left or to the right. What about the coordinate is going to change? If it slides left or right? Yeah, the x value. So when we're doing phase shifts, which is what we're doing today, we're talking about changing the x values. The y values, we're going to leave them alone because we're not doing anything up or down. So the goal now is to take that original table I gave you that had 5 points in it and do something to it so we can figure out our transformation. The first step is to copy down the y's. Those will stay the same. Okay. Just so we can remember, can someone remind me, what are my y values for sine? Just read the y values going straight down the original table. Yeah?
Is it 1, 0, negative 1?
That's how the ones for cosine start. 1, 0, negative 1, 0, 1. How about for sine?
0, 1, 0, negative 1, 0.
Yep, very good. So if you're doing a sine problem, you're going to write down the numbers that Fiorella just said. If you're doing a cosine problem, it's the ones Cameron started to say. All right, so what's going to happen to the x's? Well, I want to look at the first problem. Don't write it down yet, because we still got to write down what happens to the x's. Look at the first problem we're going to do. It's x minus pi over 2. Which way are all the x's going to get shifted in this problem? To the left or to the right? To the right. If you want to take a coordinate, it's on a grid, and you want to move that coordinate that way. What has to happen to the x value if it's going to move to the right? It has to increase. Right? If the point is going to move to the right, the x value needs to get bigger. So, what we're going to do to get something that's bigger is we would have to add. So when you see a minus here, that means everything is going to move to the right, which means you need to add to your x value. How much are you going to add? You're going to add that much, pi over 2. So just like we keep saying, it's the opposite of what you would expect. So look at your problem and determine what has been added or subtracted. In our case, we have subtracting pi over 2. Do the opposite of that. Because we just said subtraction has to push it to the right. The only way to move something to the right is to add. So we would have to add pi over 2 to all the original x values. So with this transformation, you do the opposite. With the one we're going to learn tomorrow, you do not. So somehow you have to remember when you do the opposite and when you don't. This is when you do the opposite. So on the test, really when I grade it, I'm going to be looking for two things. One thing I'm going to be looking for is a table. The new table is going to have 5 points in it. The other thing I'm going to look for is a sketch. Let me show you how you do the table. This is not the table. This is the table I already gave you in your notes right there. It's just the table for sine. I want the table for that. So when you're doing a phase shift, which this one is because it's subtracting inside parentheses, the y's stay the same. So copy the y's from the original table, which I put right up there. So 0, 1, 0, negative 1, 0. Those 5 numbers go right here. If you got at least that on this problem, you'd get 5 points. The way I grade it is I give you 1 point for each x and y you get right in the table. All right, now it says determine what has been added or subtracted. We've subtracted pi over 2. So what am I going to do to all 5 of those original x values? I'm going to add pi over 2. Yep. So what I'm going to do is I'm going to put these original x values over here, but leave a little bit of space. What I'm going to grade would be in that table. On the outside of it, I'm going to do my calculation. And the calculation is to add pi over 2 to all of them. And that's going to shift them all to the right. No decimals. Okay, so really, calculator's not going to help at all. We want to keep everything here as an answer with pi. So the first one, that's probably the most straightforward one. What's 0 plus pi over 2?
Pi over 2.
Pi over 2. That's your first one. The second one, pi over 2 plus pi over 2. When you want to add fractions together, what do you have to make sure you have first? You already have a common denominator here, so that's fine. When you add those together, the denominator stays the same. But then you have pi plus pi, which is how much? 2 pi. Now, sometimes when you add fractions up, you can reduce. Here, you can reduce by 2. I want you to see that the answer is 2 pi over 2 for a reason I'll show you in a minute. But then I want you to reduce pi. Okay, the next one is pi plus pi over 2. Well, what could we put for a denominator here? Because we don't even have one.
1.
Yeah, it's a 1. Now, are these two denominators the same?
No.
No. What's the smallest number that 1 and 2 go into?
2.
2. This one's already a 2. So you're going to have to multiply this by something to make it a 2.
2.
2. If you do it on the bottom, you have to do it on the top. So now you've got 2 pi over 2 plus 1 pi over 2. What's 2 pi over 2 plus 1 pi over 2?
3 pi over
3 pi over 2. Okay, let's do the next one. Do we have a common denominator? Bless you.
Yeah.
Don't? Yep. Grady, what's my common denominator?
2.
2. And then just add what's in the top. 3 pi plus 1 pi. 4 pi. But this is one that actually reduces. That reduces to 2 pi. And the last one. Tyler, since I don't have a common denominator, what would I put right here for I'm going to put a 1. And the common denominator would be, well, Jackson?
We have to multiply it by 2.
Yep, we're going to multiply it by 2. And now we've got 4 pi over 2 plus 1 pi over 2.
We get 5 pi.
5 pi over 2. Good. And if you got all that, you would get 10 points for this problem. 1 point for each x and y. And it'll be set up a table on the test, just like that. And as far as putting the pi symbol in, I'm going to make it so when you click on the table, the pi symbol pops up for you. Now, look at the pattern of numbers. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. What do you think the next one would be if we kept going? If you don't reduce it. 6 pi over 2. So 6 pi over 2, 7 pi over 2, 8 pi over 2, 9 pi over 2, 10 pi over 2. The pattern here is always over 2, and the number in the top goes up by 1. So what I do is once I see the pattern after the first 2 or 3, I just continue the pattern. I don't worry about finding the common denominator every time. But there has to always be a pattern. Not as easy to see the pattern once you reduce it. But you should reduce it for your final answer. So that's our table. Now, we want to graph it. Now, when you want to graph something, right, you've got to set up your number line. We talked about what that's called, scaling. The calculator scaled it to go by 90s. Why? Because that makes the points land at nice grid lines. When you set up a number line, you can go by whatever you want. The only rule is you're consistent. If you want to go by 5s, you can go by 5s. If you want to go by 2s, we can go by 2s. But you have to go by numbers that are equally spaced. You can't do this. can't say I'm going to go by 7 and then go by 3 and then go by 5. You can't do that. So we want to pick values that are equally spaced. What do we know about those x values right there? 0, pi over 2, pi, 3 pi over 2, and 2 pi. They're what?
Like whole numbers.
Well, pretend they were in degrees. 0, 90, 180, 270, 360. Yeah? Yeah, they're all intervals of 90. These are all equally spaced. So could you use these numbers to label your number line? Sure. They are equally spaced. So that would be my suggestion. Use those numbers. That's going to be the easiest way to find your points. So this is 0. I put my points a little bit lower because remember, you're going to be drawing a picture. I would not put kind of any points in that zone. You need all that space to make a picture. All right, so we got 0, pi over 2, pi, 3 pi over 2, and 2 pi. And as far as the highest and lowest on the y-axis, that's just 1 and -1. If you're going to go by ones, you don't have to label. If you want to, you can. But it wouldn't be wrong if you left off the 1, -1, and 0. Okay, now graph your points. So pi over 2, we're at 0. Pi, we're at 1. 3 pi over 2, 0. 2 pi, that's the lowest, -1. And I need one more label I forgot to put. 5 pi over 2 is at 0. And remember, when you connect dots, it's a wave. So just try to make it look as smooth of a curve as you can. That's the new graph. The original would have looked like about like that. You don't have to draw both. I'm just showing you. The original is in red, and the black one was pushed to the right. So the way I'm going to set it up on the homework, I'm going to have graph paper. It's already on the worksheet if you print it out. There's one graph that says original, and then there's one graph that says the new one. You do the red one, that'd be the original. The black one, that's the new one. So that you can see each one of them. Or if you want to do both on the same one like that, that's fine. That's up to you. Question on it? So we'll try like 1 or 2 more of those, and then that'll be phase shifts. Okay, so this is a phase shift. A little bit bigger of a phase shift than the last one. The last one we shifted by pi over 2. This one we're shifting by double that. We are shifting by pi. Okay, before I can figure out where it's going to shift to, what do I need first? Yep. Okay, I need my y values. I need my original y values because we are shifting left and right. Nothing is happening to these y's. So I need to know what they are. What are my y values for cosine? And if you accidentally do sine, well, you'll get all the y values wrong. So don't do sine. You looking it up on checking it out on your phone, Jackson? You checking out the y values for me?
Oh, 0, 1, 0, -1, 0.
So 0, 1, negative 1, 0, those y values are absolutely perfect for sine. We need cosine. But those are great numbers to keep in mind for half the problems we're going to do this week. So don't forget them. Those are good ones. But I need the cosines. Yep.
1, 0, negative 1, 0, 1.
1, 0, negative 1, 0, 1. Okay. So what I want to do now is put the original x's down, but put them off to the left because you need a little bit of space. We're going to do some work. We're going to put the final answers in that table. What are my original x's? And this time it doesn't matter if you give me sine or cosine, they're the same. Examples.
0, pi over 2, pi, 3 pi over 2, 2 pi.
Yep. And now we need to do something to all of them. Plus pi. How is a plus pi going to shift all these points? It's going to move them to the left. If you want to move something to the left, what do you have to do to the value of it? You need to subtract. You need to make the x value smaller to pull it to the left. So we're going to subtract from all of them. How much are we going to move it? Pi. So let's do the first, the third, and the fifth one, because we don't really need common denominators for that. What's 0 minus pi?
Negative pi.
Negative pi. What's pi minus pi?
0.
And what's 2 pi take away 1 pi? Pi. No reason I did those first, I just thought they were the easiest ones. Okay. Now, I've got pi over 2 minus pi. What do I put for a denominator when I don't have it?
1.
1. And what do you multiply by to fix it? 2. So you've got 1 pi over 2, take away 2 pi over 2. What's that going to be? Negative pi over 2. Because it's 1 take away 2. So negative 1. Okay, same idea with this one. Make it a 1, but then multiply the bottom by 2, multiply the top by 2. What's 3 pi over 2? Take away 2 pi over 2. That's pi over 2. There's your table. Once we have the table, now we got to think about setting up the axes. What do we know about those x values I just circled in terms of their spacing? They're what? Yeah, they're all spaced equally. If you take 5 things that are all equally spaced apart and you move them all together the same amount, are they still equally spaced? Then we can use these for our new x values. They are all equally spaced because they started equally spaced. All right, so you're going to need a couple negatives, 0, and then a couple positives. I don't know why, but some people try to change where 0 is. 0 has to be here. You can't change that. 0 is always the axis. Okay, so this one will be negative pi over 2, pi over 2, and pi. If you look at it in degrees, that's negative 90, negative 180, negative 90, 0, 90, 180. They're all 90 apart. Now, graph your points. So negative pi, 1. Negative pi over 2, 0. Whoops, I was off 1. Sorry. Negative pi over 2, 0. 0, we are at negative 1. How about pi over 2? We're at 0. And pi, we're back at 1. Now, I know the 5 points, they look a little different. Kind of looks like a V shape. Remember, though, it looks like this. What you're sketching this time looks like that. It's the low part of the wave. So try to make it look curved. Right? So something kind of like this. Don't draw it. And that's your new one. The original would have been over here, but it's been shifted to the left. Okay. Any questions on the table or the sketch? I will tell you the sketch is not worth that much. The table is going to be worth 10 points. The sketch is worth 2. So the table is the most important thing. Okay. All right, last one. So it's another phase shift. This is the smallest shift that we've done. We shifted by pi over 2, that was 90. We shifted by pi, that moved it 180 units. This is a shift by 45 units. Pi over 4. It's not a very big shift. Okay, let's make our table. And we know that it's moving left and right because it's a phase shift. So which one of these columns is unaffected? Doesn't change. The y's. What are my y values for sine? Jackson.
It could be 0, 1, 0, 1, 0.
Perfect. Okay, so you got 5 points right there. There's your y's. Okay, x's. Let's put the originals off to the side. Leave a little bit of space so you can do some work. Then we'll put our answers in the table. Can somebody remind me? Original x values. Yes.
0, then pi over 2, pi. 2 pi over 2, and 2 pi.
2 pi over 2 and 2 pi. And we are subtracting pi over 4. Subtracting is going to move them all which way?
Right.
To the right. So what do we need to do to move all those values to the right? We need to add something. And what are we going to add? Pi over what? 4. Yep. Now, with this one, I'm going to hope that maybe we can do the first 3, and then you start to see a pattern, and then we can just continue it for the last 2. If you can't see a pattern, then you're going to have to do common denominators every time. All right, first one, well, it's just 0 plus pi over 4. That one's just pi over 4. Next one, we have denominators of 2 and 4. So what's my common denominator? 4. How would you turn 2 into 4? Multiply by 2. So that's going to become a 4, and that's going to become a 2. 2 pi over 4 plus 1 pi over 4. 3 pi over 4. Okay, next one. We have a 1 and a 4. What's my common denominator?
4.
So what would you multiply top and bottom by? 4 and 4. So 4 pi over 4 plus 1 pi over 4.
Just going by 2 pi.
So what do you think the next one would be?
7 pi over 4.
Yeah. And then 9 pi over 4. And then 11 pi over 4, 13 pi over 4. Depends how much you have to keep going. But we're stopping there. Okay. Any question on that table? Now, here's where we have to be careful setting up the axes. Let's just think of the numbers in front of the pi. 1, 3, 5, 7, 9. Are they all evenly spaced?
Yeah.
Yep, then we can use them. But let's think about to put 0. Let's just say that's the start. Where does 1 go?
Whatever.
Well, let's assume like we're doing a number line like somebody in, like second grade would do. These are all going to go by ones. So where would 1 go? On the first tick. So is the next number right next to it? Should it go right here?
No.
Why not? This one went right next to that one.
Because you're skipping a number.
I got to skip a number. Okay, I have to skip a number. And the reason I have to skip a number is because I didn't have 2. I also don't have 4. I don't have 6. And I don't have 8. So when we put these labels on that axis, we have to do exactly the same thing we did right there. This is going to be 1 pi over 4. This one will be 3 pi over 4, 5 pi over 4, 7 pi over 4, and 9 pi over 4. That's exactly how you have to do your labels. If you get confused with the pi, then fine. Think of it without pi. How would you do 1, 3, 5, 7, 9? Do it the same way you would do that. Okay, so let me put, you know what, I should probably just use that other one, but this one has straighter lines. Alright, so we've got 0, 1 pi over 4. You're skipping 2 pi over 4 because you don't have a 2. Go to 3. 3 pi over 4. You're skipping 4. You're going to 5. Skip 6. We're going to 7. Skip 8. We're going to 9. It's the only thing that's a little tricky about that one, setting up your labels. These stay the same. And now from here it's easy. So pi over 4, we're at 0. 3 pi over 4, we're at 1. 5 pi over 4, we're back to 0. Yeah, I just left my labels a little bit off. 1, 2, 3, 4. Oh. So that one does go there. There we go. Fine, when you have graph paper, it'll make it easier to line things up. I think that looks good now. 7 pi over 4. That's that one. And put it about at -1. And the last one is 0. Draw your graph. You'll know if you don't space your points evenly because it might come out looking like this. If one part of it looks really squished and the other part looks really stretched out, then you know you didn't put your labels in the right spot. It should look like this. Not like that. Okay, so that's a fascia. For tonight, you will not need, well, the book's online, but you won't need the book. It's a worksheet, and the PDF is online in the lesson I showed you on school. I think it's seven problems. Okay? Make sure you make the table and you do the graph. If you don't make the table, you won't get credit.